Hey everybody, welcome back to Environmental Organic Chemistry. So today in this lecture, it's not a lecture. Let's not call it a lecture. Lecture sounds too upsetting. In this example, we will look at sorption isotherms and how to fit them using real equations. So this example problem is in Sakai under practice problems, practice problem 9.1 and sorption isotherm. This is the sorption isotherm part of this spreadsheet. And the practice problem 9.1 is the subject of another video. So I have, this is what you'll get if you click on that link and download the file. But I've taken the salient information and moved it over here so that we can look at this. So this is not a practice problem that actually comes out of your textbook. This is the one that came from my own foul little mind. And I like this problem because this is a real world example. This is something that we actually did for the lab class back in the day when I used to teach the lab class that Dr. Schaefer now teaches. I taught that thing for like 15 years. So glad I'm not teaching it anymore. Anyway, so what we did is we took some Chelsea soil, which is from Chelsea, Michigan. It's near the University of Michigan, so they use it, you know, it's nearby. So Chelsea soil has been studied a great deal. And this is a 21-day equilibrium. We could have a long argument about whether 21 days was a long enough equilibrium. It's possible that it wasn't, but we're going to assume that we're at equilibrium here. So what you do when you do the sorption isotherm is you add a known amount of Chelsea soil, a known amount of water, and a known amount of your chemical. And in this case, the chemical is phenanthrene. So that's your CO. That's the beginning amount of phenanthrene that was added to the bottle. Then after your 21-day equilibrium, you measure your concentration in the dissolved phase. That's CW. You subtract this concentration from the concentration that you know you added, and you figure out the mass of the phenanthrene that has now disappeared, and you divide that by the amount of soil that you added, and that gives your CS, the amount of the chemical that's sorbed. And of course, you're assuming no reactions, no biodegradation, which usually means you have to add something like sodium azide or something to your bottles to kill the bacteria, because over 21 days, bacteria could very well degrade phenanthrene. All right, so now we have this data, and we want to fit it to a sorption isotherm. So what a sorption isotherm is CS versus CW, right? So one way to do that, insert chart here, and then this is the extra data we don't need, so I'm just going to hit delete. Okay, so there we go. So there's our sorption isotherm, and we might want to give our axes some titles. So the horizontal title would be CW. And the vertical axis here, axis vertical would be CS. Get rid of that. Oh, I guess we could call it something. Sorption isotherm. There we go. All right, so there's our sorption isotherm. We have way too many significant figures. Drives me crazy. Let's get rid of a few of those. There we go. Ooh, there we go. That looks better. All right, so there's our sorption isotherm. What does it look like to you? Well, it looks kind of linear. One thing we could do is just right-click here and add a trend line. And I have this stupid, I have a little thing here that shows me what I'm recording, and I have to move it out of the way. Okay, there we go. So we could display our equation and our R squared on the chart. So our R squared, if we assume this is a linear isotherm, our R squared would be 0.986, which is not bad. But when you're doing this stuff in the lab, you should get a really, really good R squared because you're doing it in the lab. And one of the things you notice is that these points are below the line, and these points are above the line, and then these points are below the line. So that's a systematic error. You want your errors to be random, not systematic. So that's our first indication that maybe this is not a linear sorption isotherm. So we have two types of sorption isotherms. We have our friend here, Freundlich. Freundlich, remember, means friendly in German. And then we have our Langmuir over here. And here's the equations for them. And remember, we can linearize the Freundlich isotherm by taking the log of both sides. And the Langmuir we linearize by taking the inverse of both sides. So let's try linearizing this using a Freundlich isotherm. So we would have CW, CS. Okay, so CW, it's actually, excuse me, log CW and log CS. So let's take the log of both sides. There's log of CW. There's log of CS. Oh, too many. There we go. Okay, and then we can plot this. Okay. Put a trend line on here. Now our R squared is 0.9985. Well, that's better. That's pretty darn good, in fact. I like that. I'm happy with that. And just to be really, really uptight about it, let's add our axes titles. So that is log CW. Don't know where it went. Where'd it go? There we go. Add vertical axis label, log CS. There we go. Perfection. Okay, so I'm pretty happy with that. Now, if I'm going to use that equation to calculate my N and my KF, then I want to know my slope equals slope y comma x. There's my slope. Should be the same number I got here, 0.686. Yep. And here's my intercept. Y comma x. Boom. Booyah. Should be the same number, 3.7119. And then just for fun, we can calculate our R squared, RSQ, y comma x. Okay, so our equation here tells us that our intercept is equal to log KF. Use a little apostrophe if you want to put something in there that's not really a formula. And our slope is equal to N. So that's easy. N is 0.686. And so KF, if this is the log of KF, then KF is 10 to that power. So there's your KF. And it has some funky units because of the N exponent, so we don't usually really worry about the units too much on KF. All right, so let's say now I want to do the same thing, but I want to do it for the Langmuir equation. So for the Langmuir equation, to linearize it, I do this, 1 over CS and 1 over CW. And then this will be my slope, and this will be my intercept. So 1 over CW here, 1 over CS. 1 divided by CW, boom, equals 1 over CS, boom, and there we go. Too many. Okay, then I can plot this. Here's my plot. Now that looks a little curved to me. That's an indicator that maybe this is not the best equation. But still, the R squared is 0.98, which is, pretty good. I'm always happy when I get an R squared above 0.9, so that's reasonable, right? So now I'm going to do some magic here. Just copy these formulas. See? This is now pointing to the right thing because I didn't have any dollar signs. Okay, so my slope, my intercept is equal to 1 over CS max, and my slope is equal to 1 over CCS max times KL, right? So CS comma max is equal to 1 over my intercept right? And then KL is equal to, first we have to take 1 over the slope here. And then we have to, sorry, so that's 1 over the slope. And then we have to divide that by CS max, which we just determined up here. And there's your KL value. We should make that a capital L. L for Langmuir. All right, so there's our values. Now, let us now plot the data, not in this transformed version, but let's plot it like for reals in the right way. So here's our CW, our CS, and this is our measured, so we'll call this CS, comma, measured. And then let's also plot CS, comma, predicted. So here's CW. Here's CS measured. And here's CS predicted. So CS predicted we get from this equation. This ugly, ugly thing. This out of the way. Okay, so our CS predicted is equal to, parentheses, CS max, which is the same thing as gamma max here. So CS max times KL times CW, parentheses, divided by parentheses, 1 plus KL times CW. Okay, and then we got to put some dollar signs in here. Again, I use the F4 for the dollar signs. It's quick and easy. Did I do that right? Yeah, I think I did that right. Booyah. Okay, so that looks pretty good. Oh, but wait a minute. That doesn't look so good. So what happens if I plot this? Ooh, yow. Okay, the predicted is way off. The orange symbols are way, way off. And I'm going to just give them a line because, you know, let's make it orange. Okay, because really this is a prediction, so we could even get rid of the symbols. Marker. No marker. Let's just do a line. So clearly our prediction sucks, right? This is not working well. And the reason is because, remember I said in class that there's not really a good reason to linearize things these days. Why can't you just predict them without using a linear equation? You don't have to do this 1 over CS max crap to linearize your equation when you have powerful computers that can do cool things without having to linearize. So in a second, we'll do the same thing, except we'll do a curve fit without linearizing. But first, let's go up here and do the same thing for our sorption isotherm up here. So we've got, use the same CS and CW here. But then here is going to be our CS predicted for our Freundlich, and that's using this equation. So CS is equal to KF times CW to the n power. And again, we need some dollar signs here to make this work. Booyah. This one looks good. And wow, that one looks good too. So if we plot this, yeah, that's pretty good. Remember, the oranges are predicted. So let's go here, add a line, make it orange. No, that's not quite what I had in mind. There we go. And if you want, we can even get rid of the marker here. There we go. So our predicted line is pretty darn good. That is pretty good. Another way of determining how good the goodness of fit is to just not plot these versus CW, but just plot these versus each other. That should give you a 1-to-1 line, and you can see it's pretty damn close. So our slope is pretty close to 1, and our r-squared is pretty close to 1. So that's telling us that we have a good prediction here. The measured and the modeled are falling pretty close to that 1-to-1 line. So the linearization is doing an okay job for the Langmuir, for the Freundlich, but not so much for the Langmuir down here where it totally sucks, right? So this is one of our first indications that this is probably a Freundlich type sorption isotherm, and for Chelsea soil we can guess, yeah, it probably is. So this is our Freundlich isotherm. I may have just said a second ago that it was a Langmuir, but it's not. It's a Freundlich. All right, so for most real-world soil samples, it's quite likely you're going to get a Freundlich isotherm. So this is good. But now, just for purposes of illustration, let's ask ourselves, how could we do a curve fit here without having to linearize, without having to use, where's my linear formula? Where did it go? It disappeared. Yeah, no, that's not it either. Somewhere in here is our linear formula. Yeah, there it is. Okay. How could I do a curve fit here without doing this bizarre linearization thing? Well, what I could do, let's get rid of this predicted value. Let's just get rid of that. And let's say that I predict this value based on some knowledge of CS max and KL. And I let these be my variables that float. And I will give them, what I think is reasonable values. So we'll start with a KL of 0.02 because that's what we got down here. Sorry, that should be KL. And I'll start with a CS max of whatever this was. I'm going to paste just the value here, not the formula. Right? So if I click here, there's no formula. It's just a value. All right, so these are just starting guesses, okay? And then again, we would say that CS is equal to CS max times KL times CW divided by parentheses 1 plus, yeah, we got it. 1 plus, yeah, got it. There we go. Times, what is it, KL times CW. Let's check and make sure we got our formula right. Yeah, that seems right. And then we're going to put our parentheses or dollar signs in there. Booyah. Okay, so same idea here, except what we're going to do, we want to fit a model, and we want to fit a nonlinear model. How do we fit models? I mean, what is a linear regression anyway? Well, in a linear regression, as I hope you maybe learned in your statistics class, a linear regression is where you try to minimize the squared residuals, right? So the squared residuals, let's find ourselves a linear plot here to look at, to show you. Right, here's a plot to show you. So you're trying to minimize the difference between the point and the line. And you're squaring that difference between the point and the line and summing them all up and then trying to minimize them. Trying to find the value of the slope and the intercept that will result in the minimum value of those squared residuals. So we can do that without having to linearize. We could calculate our squared residual. So our residual is the difference between our prediction and our model. Oops, model. And then square it. Doesn't matter whether you do predicted minus measured or measured minus predicted because you're squaring it. So this is our squared residuals. Way too many significant figures. Okay. So then we can copy these all down, and then we want to minimize the sum of them. So here's our sum of our squared residuals. Boom. So this is the number we're trying to minimize because it's the sum of our squared residuals. So we can use this fancy thing called the solver. The solver says, what's your objective? My objective is this cell right here. What do I want to do with it? I want to minimize it. How am I going to do that? By changing these two variables right here. Those are the two variables I get to change. I almost always make those unconstrained variables non-negative, meaning that they have to stay positive. So I just leave that box checked. You could put other things in here. You could say that they have to be greater than 1,000, or whatever you want. You could add. So you could say this has to be greater than or equal to 1,000, and then that would show up here as one of your constraints. But I'm not going to do that, so I'll just get rid of it. Okay, so I'm just going to keep this thing that says make the unconstrained variables non-negative. I gave it my target cell. I said I want to minimize it by changing these two variables over here, and I just hit boom, solve. And then I get this thing and I say, yeah, I want to keep the solver solution, it's all good. And notice that my numbers are quite different now. I started out at 166,530 and I'm at 638,823. It's very different. My KL also changed by an order of magnitude. So now let's go back to our plot, which is around here somewhere. Don't know where I put it. Here it is. So here's our plot, and now our difference between our measured and our predicted is much, much better. There's our measured, there's our predicted, much better. So you get a much, much better curve fit by using a nonlinear curve fitting routine. And that solver feature of Excel will let you do that. You can do also slightly better job even with the Freundlich by using the nonlinear curve fit, but it's not much better, so it's probably not worth going crazy over. But why? Why does this happen? Well, because if we go back to our original isotherm, which I've lost now, it's around here somewhere. Here's our original isotherm. If we truly thought that this was a Langmuir isotherm, remember L for Langmuir, L has an L shape like that. So if you really truly think that this is a Langmuir isotherm, you need to continue these concentrations out until they level off. Because when you do the linearization, you take 1 over this concentration. So 1 over a really high concentration becomes something really small over here. And that is what is constraining the intercept. And the intercept is where you get CS max. So if you're doing a Langmuir isotherm, you have to make sure that you continue your concentrations out until you get a level value of CS max so that you can constrain your value of your intercept properly. If you don't do that, you're going to get exactly what we got before, a really bad curve fit. All right, so that's an example of how you do a sorption isotherm, and also how you use the solver feature of Excel, and also how linearization can lead you badly, badly astray if you're not careful. See you on the other side.